In modern web development, HTML, CSS, and JavaScript together form a highly sophisticated interactive environment capable of producing complex technical systems far beyond static web pages. When used deliberately and experimentally, these technologies become a programmable laboratory for creative computation, enabling the construction of musical instruments, data processes, generative visualizations, and intelligent interactive tools directly in the browser. The browser itself acts as an execution engine, a rendering interface, and an event-based operating system for sound, visuals, and logic. Every component, from DOM rendering to the Web Audio API and WebGL pipeline, can be programmatically orchestrated to build deeply technical systems. At a fundamental level, HTML defines the structural and semantic foundation of the application. CSS creates the presentation layer with fine control over geometry, motion, and color, often accelerated by GPU compositing. JavaScript provides the runtime intelligence. Event scheduling, signal generation, data processing, and algorithmic decision-making. Together, they are not limited to website construction, but can implement systems traditionally built in C++, Max, MSP, or standalone DAWs. Web Audio API exposes low-level digital signal processing nodes such as oscillators, gain controls, filters, convolution reverbs, and delay lines, which can be interconnected in real time. Tone.js abstracts this architecture into a musical layer, providing transport timing, sequencing, envelopes, and samplers capable of streaming preloaded instrument samples with deterministic scheduling. When designing a browser-based technical instrument, such as a multi-mode generative guitar ambient engine, every parameter, timing, gain, pitch, harmonic structure, modulation, and signal routing can be dynamically controlled and visualized. Tone Transport provides a sample-accurate scheduling system where musical events are quantized to time subdivisions such as 4n, quarter note, or 8t, triplet eighth. Each event can trigger a sequence of sampler notes with individual gain and duration settings. Gain nodes serve as the main amplitude control elements, and their hierarchy defines the overall mixing architecture. By constructing 3 independent samplers, each with its own gain and timing offset, polyphonic ambient textures emerge from algorithmic coordination rather than manual sequencing. A balanced note selection algorithm can be implemented by tracking per-note usage frequencies and weighting selection probabilities inversely to their usage count. This ensures that across time, each pitch in the scale appears approximately uniformly, producing a natural harmonic balance. This mechanism mirrors reinforcement learning and stochastic music generation techniques, where systems maintain diversity by penalizing repetition. By dynamically recomputing weights based on usage history, the generator self-stabilizes its tonal distribution. The harmonic engine relies on chord definitions, for example, C major, F major, G major, and a minor, encoded as arrays of note names, C3, E3, G3, etc. Chord sequences can be defined manually or generated procedurally through stochastic progression algorithms. In a multi-mode environment, modes such as Ionian, Dorian, Phrygian, Lydian, Mixolydian, Aeolian, and Locrian alter the pitch set by applying interval transformations relative to the major scale. This can be realized by transposing selected scale degrees, e.g., lowering the 2nd and 6th degrees for Dorian mode. A drop-down interface can allow users to switch the tonal mode, which dynamically rebuilds both the chord dictionary and the balanced note set. The user interface acts as the control surface of the digital instrument. Range sliders, drop-down selectors, and buttons map directly to signal graph parameters. For instance, tempo is bound to tone, transport.bpm, value, duration is expressed as fractional note length multipliers, and gain sliders directly modify the gain node values. Solo buttons can temporarily mute all but one signal chain by setting the gain to 0. Reset functions restore all parameters to default equilibrium values. The interface feedback loop, consisting of text indicators and visual states, provides the user with live insight into current pitch, gain levels, and playback status. Implementing this in a browser requires precise scheduling and resource management. The web audio graph should be created after user gesture events, click or touch, because browsers require user interaction to unlock audio contexts. Each sampler must preload its sample set, typically hosted via public SoundFont repositories. Samples should be normalized to consistent loudness levels to avoid amplitude imbalance. Transport events are scheduled via Tone. Transport, schedule repeat, which receives a callback function and a repetition interval, in seconds or musical time. Inside the callback, each piano or guitar sampler triggers multiple note events within the defined time window, resulting in layered rhythmic polymeter textures. From a system architecture perspective, the web audio engine can be viewed as a real-time DSP network. Each gain node, filter node, or sampler node represents a node in a directed acyclic graph. Data flows downstream as digital sample streams. Parameter automation modifies the coefficients controlling these flows. Time synchronization is ensured by the transport's high-resolution clock, which internally aligns event scheduling to the audio context time domain, avoiding drift that would occur with standard JavaScript timers. A technically comprehensive implementation also includes state persistence and parameter automation. Using local storage, user preferences such as gain levels, tempo, or selected mode can be saved and automatically restored upon reload. For real-time visualization, Canvas or WebGL can render oscilloscopes, spectrum analyzers, or chord matrix diagrams synchronized with the audio transport. This adds a multimodal feedback layer, converting invisible sound events into analytical data. Furthermore, integrating MIDI input through the Web MIDI API allows direct external control. Physical guitar or keyboard input can drive sampler triggers or modify real-time effects. To extend realism, an effects chain can be introduced. A convolution reverb node with impulse response loading, a stereo delay unit synchronized to tempo subdivisions, and a chorus or phaser module for spectral motion. Each of these effects can be encapsulated as reusable processing units within the Tone.js framework. The signal chain would then become sampler right pointing arrow gain right pointing arrow FX chain right pointing arrow master output. Each FX node exposes parameters, wet, dry mix, decay time, feedback amount, that can be automated or modulated by LFOs, low-frequency oscillators, allowing generative timbral evolution. In pedagogical terms, this system teaches multiple concurrent technical domains: audio synthesis, time domain event scheduling, probabilistic algorithm design, and interactive user interface engineering. Students experience how a minimal HTML environment can host high-level musical computation without plugins, compilers, or native binaries. This paradigm redefines web coding not as front-end decoration, but as a platform for algorithmic creativity and technical exploration. From a performance optimization perspective, careful attention must be given to garbage collection and scheduling overhead. Pre-allocating node sequences, preloading buffers, and using efficient lookup tables avoids CPU spikes. Parameter updates to Tone.js nodes should use smooth transitions, ramp to, instead of abrupt assignments to prevent audible clicks. The UI should throttle slider events to avoid flooding the audio engine with parameter changes. Conceptually, this type of system demonstrates that in-browser programming can rival standalone digital audio workstations in precision and expressiveness. The combination of web audio, WebGL, and high-resolution timing transforms the browser into a self-contained digital laboratory for computational art, research, prototyping, and generative design. The same principles apply beyond music. These algorithms can structure dynamic data visualizations, procedural animations, and intelligent simulation systems. Each module, whether a sampler, oscillator, or chart dataset, becomes an abstract programmable component linked through deterministic timing. Ultimately, this approach conveys a fundamental insight. HTML and JavaScript are not limited by their original web design heritage. They are universal computation layers capable of hosting interactive, algorithmic, and sensory systems.